Continue to discuss tensor networks. There was an example number 1, a product state, a trivial tensor network that we discussed yesterday, and today we'll continue with example number 2. And this was a quantum circuit of finite depth T, meaning that it's a quantum circuit made of T rows of gates, as in the drawing. Okay, and we want to see whether this is an interesting tensor network. Okay, remember anybody can come up with a bunch of tensors, connect them together, and the question is that useful at all? And so we had 3 rules. We wanted to see 3 properties of a tensor network before we could start deciding whether it was useful or not. The first one was efficient specification. So A, we have an efficient specification. Okay, and what we're going to do in this case is we're going to count what we have, how many parameters we need in order to specify this quantum circuit. So, and we briefly discussed this already. So how many gates do we have here? Well, number of gates is equal to, roughly speaking, it grows as n times t, okay, because we have t rows, and on each row we have on the order of n gates, maybe n over 2. Okay, so we said t is fixed, so that and then number of parameters or coefficients in each gate. I don't know. A gate would be a unitary transformation on 2 d-level systems. So each gate has on the order of d to the 4th parameters if each line here contains, if each index I1 goes from 1 to d, then these gates are d times d times d times d, d to the 4th. Okay? So that's a constant with respect to n. And so what we have is that indeed the number of coefficients or parameters, so we have order n parameters, okay, coefficients, total. So again, every time we want to consider a larger system, we just need to add a constant number, in this case proportional to t, a constant number of parameters to specify the wave function in with an extra site. Very good. So, but remember that efficient specification was not everything. We need to know whether we can efficiently extract information. Okay, so B, remember, efficient manipulation. Okay, so typical things we want to be able to compute. Maybe it's the norm. And remember, you have all these drawings in the notes I sent you for yesterday's lecture. So how much is the norm? Well, if this is a gate, so here what I did is this part here represents psi as a ket, and this is psi as a bra, and we multiply them together. That's done here. Okay, so that's a scalar product. But if this is some gate u, unitary gate, and this is u dagger, they cancel. Okay, so this cancels with this cancels with this with this, and then there is nothing between this one and this one, but this is some v, and this is v dagger, and there is nothing in between, so they cancel, and so on. So everybody cancels. Okay, and we're left with this. So we start with the scalar product of a product state with a product state, which we know how to efficiently evaluate. And in this case, if this were normalized, it's already 1. Okay? We are saying nothing but that if our wave function is u applied to 0 to the n, okay, then of course psi is this 0 to the n u dagger. That's describing this guy. U now represents the whole circuit, So then the scalar product is trivial because this, times 0 to the n. The quantum circuit part disappears, and you're left with the scalar product of the 0 times n. Okay? No surprises there. Very good. So if and this is some lesson we can take with us, if our if our tensor network is based on a quantum circuit, the normalization of the state comes for free. It's by construction 1, okay? Because all the gates that define the quantum circuit will disappear when we multiply psi with psi dagger. Very good. But what about the next step? What about the expectation value of some local observable? Okay? And for that, what I'm going to do is, here you can imagine the whole circuit for psi is in here, and for psi dagger is in here again. I just didn't draw all the gates. And then what we want to do is this observable, it's going to be some matrix acting on, say, whatever, the 7th aside. So 1, 2, 3, 4, 5, 6, 7, 1, and so on. Okay? So this is the quantity we want to evaluate, and the question is whether we can efficiently evaluate. This is a number, it's a tensor network with no open legs. Remember that there are zeros all over. Okay? So there are no open legs. So it's a number, a complex number. And the question is how much it is, or how expensive it is to actually compute it. And you can go to figure something in the notes. I think you have it in figure 5, okay? And you see the details of what's inside here. But the idea is that, again, there can be many cancellations. So there won't be a cancellation between the gates which are immediately next to. So if we have an operator here, this gate cannot cancel with this one. This is U dagger. They cannot cancel because there is something in between. But next to it, this V and this V dagger, again, can cancel. Okay? And there are many cancellations, and that's roughly the pattern that you are left with. So there are cancellations outside what we call the causal cone. Causal cone of this side here. Okay? So when we want to evaluate this expectation value, we have a complex tensor network that you have in the drawings in figure 5. And there is an important simplification. All the gates which lie outside the causal cone disappear. But you are still left with that. And in more detail, it looks like something like this. Okay? Very good. And now what we need to do is we need to understand how to contract. This is still just a number, but what we are provided with are the individual gates and this operator sitting here. Okay, and well, and then it's not so simple, because if you want to contract this, you'll have to proceed in some way. You'll have to take tensors, multiply them together. Okay, and what you will realize is that when you multiply two tensors together, the resulting tensor might have more indices than you started from. So for instance, if we try to multiply, say, these two tensors together, okay? This one had 2 legs, this one had 4 legs, but the result has 1, 2, 3, 4, okay, 4 legs still. So let's try another one. That didn't come out right. So yeah, so you are done with this one, you are done with that one. Now you try to add an extra one, and then you see that the resulting tensor has 1, 2, 3, 4, 5, 6 legs, okay? So as you try to contract all these individual small tensors together, there is no way to avoid creating bigger and bigger tensors, okay? And that's a result. There is a result that says that if you try to contract this together, remember this, you have T tensors or T rows of tensors in this direction. By this linear effect here, you can see that this is also going to be order T, right? Remember, the whole circuit had n legs, n, but when we look at the cancellations, lots of legs disappear, okay? And we're left with something that has only order T tensors in this direction, okay? And then it turns out that doesn't matter how hard you try to contract this together, there is a cost which will be exponential. So cost of contracting this is exponential in T, okay? Which is okay because T is a constant. We said the constant depth quantum circuit, but let's just keep in mind that there is a complexity cost associated to contracting this, which is exponential in T. And this will be important later. Okay, but that's it. Then that's the total cost is independent of n, okay? So that's efficient. We can consider now a very large system, and the cost, so n can grow a lot because we have an efficient specification. We have an efficient way of extracting local observables. So we're happy. Okay? The only question is, what is this useful for? Right? That's part C. Okay. So to understand what this is useful for, what we will do in this lecture is to look at what is the scaling of entanglement entropy, what's the scaling of correlations, as we did for the product state. And just as a means to get some intuition of what type of states can be represented with this tensor network. So, see, is it a good approximation? To ground states of local Hamiltonians? And again, we cannot answer yes or no to this question. We can just build some intuition. We can see whether this class of states will have correlations and entanglement that scale compatible with what we know in ground states. All right, so let's look first at correlations. So what I want to do here is to compute an observable on some site L, an observable on some site M, okay? And this one is going to be this one. And this one is going to be this one, okay? And again, you have the drawings in detail on figure something, I guess 6. Let me check. Yeah, figure 6. So what you have here is the whole quantum circuit that I didn't draw. That represents, again, psi, dagger, and these are the two local insertions. And again, what happens is we have the same type of simplifications. So away from the so-called causal cone of the two operators, there is no abstraction for this gate here, u, little u, to annihilate with u dagger. Okay? So this will annihilate, will disappear, and this will happen throughout the tensor network, except inside the causal cones. And so we will have a situation like this, and then we can remove the lines that, contribute a 1, right? This line contributes a 1 to the correlation function, so we end up with this, okay? But now the important observation is that this looks very much like that, okay? So this is actually exactly what we would obtain if we were computing, again, the expectation value of O of this insertion alone times the expectation value of the other local operator. Okay? So, and we know what this means. This means, again, that if we take this minus that, we'll get 0. Okay, so the connected correlators are, again, 0. Okay, question?
If your operators that are close enough, though, and they share a causal past, you wouldn't get non-trivial correlations then.
Exactly, very good. So here, I started assuming that these guys were far away. How far away? Well, I knew that this is going to spread t half in this direction. Right, this is t half, total t, right? So this is also t half in this direction. So I assume what we can say right now is that correlations, let me write this. Let's write it this way. Insertions in positions L and M minus expectation values on L. What we've shown is that this thing is equal to 0 if the distance between L and M is larger than t. That's what we've shown, right? But this is potentially non-zero, potentially, right, for shorter distances. So when L minus M are smaller than t. Okay, exactly, very good. So what we see is that this state already has non-trivial correlations at short distances. And then a sharp cutoff at some longer distances given by t, we're done. We have something similar to the product state that we had analyzed, okay, at longer distances. But there are non-trivial correlations within a finite neighborhood. So that's good. That's good. Excellent. And then finally, we want to compute entropies. We want to understand the scaling of entropy. And so for that, we need to compute the reduced density metrics, and this is figure 7 in the notes. Okay? And we again have the quantum circuit psi. Well, let me first tell you something that we can announce it as a theorem, and then in the tutorial you'll see in detail. But so let me call it theorem. It's not very hard to prove. That if you have a wave function of two parts, A and B, and you can write it as a single sum from 1 to some number n of whatever you want to throw in, some states in alpha, and some in part A, and some states in part B, okay? And this is not the Schmidt decomposition, okay? Not Schmidt decomposition. Okay, remember that for this to be the Schmidt decomposition, this should be an orthonormal basis or an orthonormal set, and also this one. Okay, and I'm not requiring that here. And here you can put some coefficients just because we are used to seeing coefficients. Otherwise, we can absorb them in the states. Since they are not normalized, they could, yeah. Okay, so suppose you have some decomposition of some form of a state, psi, then in terms of m terms, okay, then it follows, that's the theorem, it follows that the Schmidt rank is at most m, okay? That's the theorem. Okay? The Schmidt decomposition is the most compressed possible decomposition you can have. It will have the smallest number of terms, okay? So that shouldn't be too shocking, but you can think about it later during the tutorial. You will have to think about it. And then, of course, it follows from here. We know that if we have the Schmidt rank gives us an upper bound to the entanglement entropy, so it follows that rho A, okay, which is smaller or equal than the entropy of the flat distribution for this. So that would be, remember the entropy on if we just had chi different eigenvalues for rho A, the entropy was at most log 2 chi. Okay, you probably remember this, but this is upper bounded by log 2m. Okay, so what I'm saying is every time you see a decomposition of a state, a bipartite state, into a number of pieces, and this number of pieces already give you an upper bound to the entropy between A and B. Okay, all right, is that clear? Okay. So, and you'll see this in detail in the tutorial, but at least I want to announce the basic result. Okay, so now we're going to use that property to upper bound the entropy that this quantum circuit can carry, the tensor network based on a quantum circuit. And what we're going to do is we're just going to diagrammatically compute the tensor network representation for rho, starting from a tensor network representation for psi and psi dagger. Okay, and so figure 7, you go there, you see that here what we're doing is this is rho in the sense that we have, how do we define rho for some region A? So let me say A is the region here. Okay, so I left those indices uncontracted, and I've taken the trace over the complementary of A, which means I've joined these indices. Okay? Is that clear? That this is already a tensor network representation for rho, but we want to simplify it a little bit. What we have again is that, well, a gate here cannot be simplified with a gate there because there is no contraction. But if you had a gate here, it will be simplified with a gate there and so on. And before you notice, what you are talking about is just working with a causal cone again. Now, instead of one point, or before we had the causal cone of a single point where we had the insertion, now it's the causal cone of a region, okay? And what we say is all the gates outside this causal cone go away. And so we end up with a tensor network that now looks like this, okay? And now you can flip it over, whatever, it will look like that. The important thing is that what we have here is, this is our density matrix. There are upper indices and lower indices, okay? And what we have is analogous to this result here, okay? Is that if, remember that the Schmidt rank is the same as the rank of the reduced density matrix, how many non-zero eigenvalues we have in the density matrix. And so there is an analogous result that says that the rank of rho, okay, is upper bounded by how many connections you have between the upper part and the lower part. So basically what I'm saying is that if this is rho, if I can represent rho in this way, where this index here takes m values, okay, suppose you have a decomposition of rho as the product of two pieces, two matrices, where the index in between takes at most m values, then it follows that in the eigenvalue decomposition, we'll have at most, which has chi values. Chi is again, so if exists decomposition for rho of this form, okay, with m values in between, it follows that chi, the number of the rank of rho, okay, is upper bounded by m. It's just the same theorem as before. Remember that there was a relationship between the signal value decomposition of a matrix and the eigenvalue decomposition of that matrix times its adjoint. We saw that. So it's the same theorem. And therefore, so we're saying the rank is upper bounded by m, but then it also implies that the entropy of rho is upper bounded by log 2m, okay? And that's the same discussion that we just had there, okay? Very good. So when you see an explicit tensor network representation for a density matrix, which is made of one piece connecting the incoming indices and one piece connecting the outgoing indices, and you can cut this representation into two pieces by some thick index, in this case, the product of these three indices and those three indices, okay? Then you already get an upper bound on the entropy of this density matrix. What we're saying is that basically that it's a thick version of this, right? We're saying we have 4 indices here, 4 indices there, and then in between there are 6 indices, okay? So there is some m here, which is the total number of values that these indices can take, okay? And this will give us already an upper bound to the entropy. So in practice, what this means is that if each index, remember, has d values, it means that we have that our m is d, in this case, to the 6, okay? Or in general, it's going to be d to the number of indices, d to the number of indices connecting the bra and ket part of our wave function. And so when you take the log of that, it's going to be this number of indices times log d. So let me summarize what I said. I said, when we look at a density matrix, if we look at how many connections we have between the bra and ket part of the density matrix, okay, this gives us an upper bound on the entropy, okay, of this density matrix. And I also said, if these connections are made of a product of indices, okay, when you take the log, so this means if you have a product of indices, each index, you'll have a power. The rank is going to be upper bounded by a power of how many values each index can take. When you take the log of that, the number of indices come linearly, okay? And the final result is that the entropy the entropy of this density matrix is at most proportional to the number of indices that you have to cut between the bra and ket parts of the density matrix. So every time you see a tensor network for a density matrix that connects the upper part and the lower part by some finite number of indices, this number of indices is the one directly giving you an upper bound to the entropy. Okay? Again, you'll see this during the tutorial, but we can apply it here. What we're saying is, well, at most in this construction, there will be a number of indices here, which is the number of indices will be proportional equal to t, or proportional to t. Okay? If you think about this construction, you'll see that these causal cones go up at most t steps. So we have that the number of indices is order t times 2, because they are on both sides. And therefore, the entropy of rho is at most, okay? So the final result is for our construction, for quantum circuit of depth t, the entropy of a region of size L is at most this. You know, we didn't have to specify how long this region was, so we get the same bound, is equal to order t or 2t. Let's say 2t times log of the local dimension. Okay? So that's the result we wanted to see. When we have this quantum circuit of finite width, the finite width of the circuit automatically implies that for large regions, the entropy saturates to a constant. Okay? And this constant is at most 2t log d. Very good. So now we want to put these two observations together and try to decide what this quantum circuit could be useful for. Let me do that here. So the summary is that correlations look like, you know, let's plot log L versus a correlator, okay, or log of the correlator, as we did for. So if this was, if we had a power law, right? This would be power law. What we have is that would be for ground states of gapless systems, we had a power law, or we had an exponential decay for gap systems. So this is gapless, and this is gapped. Okay? And remember the entropies that we had. We had, if we plot them, S of L versus log L, again, as in upper, we had a log L for critical or gapless, and a saturation for, so constant, for gapped systems. Okay? And now the question is where this quantum circuit fits. And so what we see is that at short distances, so we'll have a strong cutoff. At short distances, maybe everything is possible, because these gates, for the correlations, at short distances, we have not said anything about what happens. But we know that this drops to 0, 0 actually is very low. But it is plausible that at short distances, we might be able to approximate whatever we want, okay, at short distances, but definitely not at longer distances. What about entropy? For the entropy, again, at short distances, we might be able to approximate things, but at some point, it definitely becomes constant. Okay? So what we see is that, in principle, if at short distances we use properly the gates, in principle, we could still get all the way to where the exponential kicks in, and then maybe it's OK if it's an exponential to replace some exponential decay with 0 correlations. Okay, that's what the exponential decay of correlation is telling you, that they become negligible very fast. So we might be able to actually, if we have, so maybe if we have a gap system, if we have ground state with a finite correlation length, okay? So gap system. Maybe our quantum circuit will be able to reproduce its properties accurately, maybe. Okay, definitely not for a gapless system because there is no way we're going to be able to replace a power law decay with a zero. And there is no way that we can replace a logarithmic scaling of the entropy with a constant. Okay? Now, let's leave it at maybe, but the observation is that there is a relation between the correlation length, that is the distance until we need to keep non-trivial correlations and non-trivial growth of entropy. There is and the T that we had in our quantum circuit, right? So remember, the quantum circuit was doing well for correlations for distances smaller than T, okay? So what we see is that actually the correlation length should be on the order of T, okay? So if you are far away from a critical point, the correlation length is small. Maybe a small t is fine. Remember, the most important part was the cost. The cost was exponential in t because we had to deal with that tensor network up there. If we wanted to compute an expectation value, we had to contract all this t times t tensor network, and that had a cost exponential in t. Okay? So what we're saying is, if the correlation length is small, that's fine. Okay? If the correlation length starts growing, well, that's also fine. The cost is going to grow exponential in this correlation length. Okay. So, as far as n, the size of the system is concerned, there is no problem. Okay. It's just that you would not want to use this to approach a critical point because the computational cost would explode. Okay, as you reach the critical point. Very good. So actually, this tensor network is pretty useful. Okay, in the end, we can efficiently specify it, we can efficiently manipulate it, and in principle, it could approximate well, the scalings that we obtain for the entropy and for the correlations are compatible with an approximation to ground states of gap systems. Very good. But there is this thing that is a bit annoying, which is that the computational cost grows exponential in the correlation length of the system. So now what we want to do is we want to find a much better way of approaching, of having correlations. So what we want is to have a tensor network that can get correlations at longer distances without a cost that exponentiates the growth exponentially in this correlation length. And that's going to be the matrix product state. Okay, so we've seen one concrete example of tensor network, or two simple examples. And now what we want to do is to study one of the most important tensor networks that we have, which is matrix product state. And so first the definition. So again, remember we have a wave function on n sides, and we can expand it. And then this time, so this defines some tensor. And this time what we're going to choose is to connect, to use a tensor network that looks like this. We're going to consider an array, one-dimensional array of tensors. We'll connect together n tensors, and we're going to call this matrix product state with open boundary conditions. And we have another version of this, which is where we connect also the last and first tensor. Okay, and we're going to call this with periodic boundary conditions. Okay, and let's make sure that we understand what this is doing for us. So let's consider an example, n equal to 5. I'm going to give names to the tensors a, b, c, d, and e. Okay? And I'm going to consider this with periodic boundary conditions. And so this is I1, I2, I3, I4, and I5. Okay. And so each tensor here, say A, but also B and C and so on, they have 3 indices. Okay? You see this is alpha, this is beta, and this is I1. That's tensor A. And the same for the rest. And so we can think of this tensor as a collection of matrices. We can think of this tensor as some matrix alpha, beta, A1. So the name of the matrix is 1, A1. And then we have another matrix A2. And then finally we have matrix D, AB. Okay? So we have D matrices. Attached to each side on our lattice we have D matrices. Very good. And so now what we would like to relate is how much is a particular configuration of our tensor. Remember, this wave function can be expanded in d to the n coefficients. And now we want to compute a specific one. So let me say we want to compute the 1, 1, 2, 1, 3. Okay? So let's see how much this coefficient is in terms of the tensor network. And so what we have to do is to go and in the first side we put matrix A1, this one here. Okay? On the second side, the corresponding B1. There's a 1, 1, 2, 1, 3. So the next one is C2. The next one is ABC, D matrix 1, and E matrix E3. Okay? So what I've done is I've just specialized this tensor network to a particular choice of values for these indices. Okay? What this looks like now, what does it look like? What is this? Number. It's a number, but it's expressed in terms of matrices as a trace of a product of matrices, right? So this is product of matrices, trace of product of matrices. Okay? So product of matrices, matrix product state. Okay? That's why it's called matrix product state, because the state is expressed, the components of the wave function are expressed as products of matrices. Okay? But I hope that it's clear then that we've managed to encode exponentially many coefficients, d to the n, okay, using just sets of matrices. We have the matrices on position. I mean, we can call this a tensor or a set of matrices, okay, or D matrices. Very good. So, efficient specification. Can we efficiently specify? So, question A. Now we have to look at the 3 questions. Okay, this A is not this tensor. So question A. Do we have an efficient specification? Well, let's count, right? Each tensor, so each tensor, how many parameters do we have in each tensor? I'm going to say that alpha, beta, etc., the Born indices run from 1 to some value chi, okay? And we know that the physical indices, I1, I2, etc., run from 1 to D. So each tensor, right, let's take again A, alpha, beta, and I, 1. How many parameters do we have there? Okay, so I'm going to say the size, okay, of this tensor is chi squared d. And how many such tensors do we have? Okay, so total coefficients total number coefficients is equal or order n chi squared d. Okay? So there we have our efficient representation. Very good. But we've learned that efficient representation might not be the same as efficient the ability to extract information. So we need to address the next question. Can we efficiently manipulate this tensor network? Okay, so B, efficient manipulation. And this time, with the quantum circuit, take psi and psi dagger, and the norm comes for free. But here, the norm is not going to come for free. You'll have to compute it. So scalar product of two MPSs. And what we see is that, and now I'm going to switch to open boundary conditions just for simplicity, but it's not fundamental. This is the ket, then the scalar product looks like this. If this is the bra. Okay? So this is a tensor network that represents a scalar product, or the norm, in this case, a scalar product of a MPS. Okay? And there are many ways of building this, but here's what you don't want to do, okay? Don't do this at home. Don't multiply these tensors on top together. Because if you do that, you are building psi, okay? And then you could multiply the ones down there. You're building blanket, okay? Congratulations, you just spoiled it, right? Because the whole point of building a tensor network was to never have to build this guy. This guy depends on d to the n coefficients, okay? So that cannot be the way of computing this scalar product, okay? The strategy is different. The strategy is to actually identify that what you have here, after some coarse-graining, is a product of matrices. A sequence of products of matrices. So how do we want to see this? Well, so let me first discuss so if we had a vector times a matrix times a matrix times a matrix times many matrices, okay? And eventually we stop. The cost of this, if we have n of those, and if this index takes only, say, chi values, okay, and this also chi values, and so on, what you see is that you can proceed, say, from left to right. And at each given time, you just have to take a vector, which is what you have here, times a matrix. Okay, so this takes chi values, and this takes chi values. And the cost of multiplying a vector times a matrix is only chi squared. Okay? Now, once you've multiplied these guys together, what you have is a vector, and then you can multiply the next matrix. And the cost is going to be chi squared. Okay? And you have to do this n times, and so computational cost, and by this I mean how long it takes, okay, it's going to be n times chi squared. Okay? So every time you see a row of matrices that have to be multiplied together, you can smile. You finally got, you're in a safe place. Okay? If you had a two-dimensional structure, if you had to multiply tensors in 2 dimensions, that's not good. There will be an exponential increase of the cost in the linear size. We saw that before when we had some form like this, where this was t and this was t. Okay? There's a cost. If you try to put these guys together, you realize that as you start, that you have to group you can proceed however you want. Okay? That you will be building a bigger and bigger object. And there will be an exponential. The object that you'll have to build will be exponentially larger in the linear size of the system, or of your network. And so 2D, bad, 1D, good. And that's what we want to see here. We have a one-dimensional structure waiting for us. So what we can do is we can simply multiply, first multiply these two together, these two together, these two together, and so on. Okay? And these are always small multiplications, so the rule here is it's okay to do many small multiplications, many order n, that's fine. And after that, we just had the situation that I described there. Okay? But this index now is doubled, and so this is a chi-square times chi-square matrix, so have to change this with a 4 and whatever, right? But it's okay, it's a constant, right? So what I'm saying is that if you want to multiply this scalar product, you can view this as a vector, this is a matrix, and just proceed from left to right. And with order n and some power, say chi4, you'll be done. Okay? That's just to give you the idea of what you want to do. But in practice, you don't really need to well, there is in the tutorial, you'll see that actually you can reduce this by being a bit smarter. It's linear in n, but there will be a reduction from chi to the 4 to chi to the 3 times the local dimension or something. Okay? So it can be reduced. But the main idea is that you have a sequence of matrix multiplications or vector matrix multiplications. Very good. So efficient manipulation. Well, at least we can compute the scalar product efficiently with order n. Okay? Next question. What about the expectation value of a local observable on site 3? Well, we're going to write this. It's going to look similar to what we had just a moment ago. Okay? So we have an insertion now on site 3. Okay, you can think that this is just one part of, say, you're trying to compute the magnetization, right? So this could be sigma z or sigma x on site 3. Okay, this was a qubit system. Very good. So how do you proceed with that? Well, this tensor network is not the same as this. But what you realize is that these are just local details. So what you could do is you could take these two guys together. Let's look at the cost of this. This is chi, d, and d. So you know that to multiply these two tensors, and that's something we discussed last week, but you'll also see it in the tutorial again. If you want to know the total cost of multiplying this, you just multiply the size of the indices. And so the cost, the computational cost, is going to scale as chi square d square. Okay? So it's there is no n system size anywhere, right? It's a local thing that you do there. And after that, what you do is you can replace this with the result of this contraction, which I'm just going to symbolically draw like this to remind us that this tensor is the product of two. Okay? And now you look at this tensor network, you look at the one we just analyzed, and as far as the tensor network structure is concerned, they look the same. So you could, again, multiply these tensors together. You'll have vector times matrix multiplications. And so the cost is going to be exactly the one we discussed before, except that you can reduce the power of chi. So this is going to be order n chi 3d again. Okay? So what we see is that we have a wave function that we can efficiently normalized, and then we can efficiently extract expectation values of local observables from it, and so on. So what we want to do, in addition to this, is to, okay, so with the time we have today, I want to explain how to even get rid of n in the computational cost. So we want to be able to study infinite systems, okay? And then we'll stop for today, and tomorrow we'll look at the entropy and a number other things. So consider a Hamiltonian that commutes with the translation operator. Okay, so imagine periodic boundary conditions. We have a chain with periodic boundary conditions, and a Hamiltonian, our local Hamiltonian, that commutes with shifts by one side. Okay, so the translation operator is the one that we considered also in previous weeks. And assume that the ground state is translation invariant. Okay, that basically means assume that the ground state is unique. Right? If the Hamiltonian is commutes with translations and has a unique ground state, then the ground state has to be also translation invariant. Very good. Then we can attempt the following tensor network or MPS representation could be of interest. Okay, we could consider the following. We could consider not taking different tensors, but actually considering just the same tensor appearing everywhere. Okay, so this tensor is full of variational parameters. Still, we haven't said what is in there. We know that there are chi-square-d parameters, but we don't know. They are complex numbers at this point. But now we are assuming that we copy the same parameters, okay, n times. Now, how much, how much is how many parameters do we need to specify? Well, I just said it, right? So we have a wave function on n spins that we have completely specified just with order 1 when it comes to n, right? It's independent of n. Constant number of parameters has completely specified the wave function. We didn't even say how much n is, right? So that's good because we can use the same tensor on 100 sides or 200 sides or infinitely many sides. Okay, we're ready to really take the thermodynamic limit. Okay, but this is efficient specification, so A, happy, specification good. Now part B, how about extracting information? How can we extract information here in a way that we do not refer even to or the cost does not scale with the system size? And so the first question is then, how do we compute the norm? Okay. Good. So how much is this? How do we extract this without a cost that is linear in n? That does not even depend at all in n. Well, let's make the observation that if we define a transfer matrix, this is A star, okay? This is A star, but this A is everywhere, right? So let me call this T, then what we have is that this is the trace of T to the n. Okay? The norm of the state is trace of T to the n. And now what we're going to do, so yeah, this is we'll refer to this as a transfer matrix. Or MPS transfer matrix. And now what we'll do is what we did also already when we studied partition function during the first week. We're going to look at the eigenvalue decomposition of this matrix, and we'll re-express this norm in terms of the eigenvalues of this transfer matrix. Okay? So remember that given a matrix, okay, is what we call eigenvalue decomposition. Okay. Let me write it in standard notation. Given a matrix M, we can decompose it as a sum over some index alpha of its eigenvalues, lambda alpha, and then right and left eigenvectors. Okay, so this is, if you want, this is the eigenvalue decomposition. These are the eigenvalues. And these left and right eigenvectors, they fulfill that they are by orthonormal basis. Okay? So in general, for a generic matrix, we cannot demand that the right eigenvectors are on orthonormal basis or the left eigenvectors are orthonormal basis. All we can demand is that between them, between the left and right eigenvectors, they fulfill this condition. And then you can quickly check that indeed, if you go here with what we just called a right eigenvector, say r beta, okay, then you replace them with its decomposition. Okay, and then you see that there is a delta here, and this is indeed, well, there is no sum anymore. This is lambda beta, and the eigenvector, right eigenvector. Okay, so all we need for this condition to fulfill that M on R on the right eigenvector gives you the eigenvalue times the right eigenvector. All that we need is this relation here. It doesn't tell us anything about the right eigenvectors to be orthonormal or anything like that. And the same occurs if we act with the left eigenvector. Okay, so in tensor network notation we could draw it like that. So we say a matrix is a sum. It's convenient to use some mixed notation in this case where we explicitly write the sum over alpha, and then these are vectors. Okay, left and right eigenvectors. So what we want to do is to just come here. If this we call the transfer matrix, I see that I've already used T. So let me call it M, transfer matrix M. Then that's automatically going to be given by sum over alpha of lambda alpha to the nth power. Okay? And now if we assume as we will, that lambda 1 in modulus at least is, in absolute value, is larger than lambda 2. And then that they are organized in decreasing absolute value. Then we can, this is lambda 1 to the n, plus lambda 2 to the n, plus lambda 3 to the n, etc. But with this assumption, then we have this is lambda 1 to the n, and when we write it in this way, it becomes clear that this is a 1 and that the contributions that come afterwards are exponentially suppressed in n. Okay? So the norm or the scalar product of our vector is lambda 1 to the n. Okay? Up to corrections that will not matter when we take n to infinity. So with that in mind, what we can do is to well, we are ready to answer how much the norm of this state is with a cost that does not depend on n. We just take the transfer matrix, right? It's here. okay? Is chi, 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 and d values. We multiply this together. There is no n. There is no system size involved in this calculation, so that may be of order chi to the 4. And then, with that, we eigenvalue decompose this matrix. We get the eigenvalues, and we take the biggest one, and that's the norm, right, to the n. So what you can do is, you don't want this norm to explode, so you can just take your, you can, from A, you can normalize it by taking A, the normalized A, this tensor, okay? You have a tensor A, you want to normalize it. Well, you define the normalized tensor as A divided by the square root of lambda 1. And if you do that, if you use now this NPS, which is characterized by a single tensor, then the norm in the thermodynamic limit is going to be 1, okay, by construction. Okay, so we've done this with a cost that does not depend on the system size. And the last comment then is that now we are ready to evaluate expectation values of local observables. Because what's going to happen here is that now we want to evaluate some observable on some site, say 0. Okay, that's going to look like this big mess. Okay, and then we have some site 0 here. We'll make this insertion. But what we see is that this is equal to trace of the transfer matrix to the n minus 1 power times some new matrix in here, okay? Times some matrix P. But we can again evaluate this guy. We can replace it with its eigenvalue decomposition. And so in the end, what this looks like is sum over eigenvalues to the n minus 1 power, and then the trace of the corresponding eigenvectors. We have the right alpha and left alpha times p, okay? Or we can rewrite this in terms of the trace. Well, trace we can just, we can just evaluate it like that. Okay? Or in tensor network notation, what we have to do is, this is the left eigenvector, this is the right eigenvector, and then we have the P is nothing but A star. We have this little tensor network, okay? Left alpha, right alpha. All we need to remember is that there are a number of terms. So if the bond dimension goes from 1 to chi, there will be here at most chi square terms. And again, in order to compute this, we don't need to do something that has cost proportional to the system size, right? This thing here is some tensor network. Will have some cost, maybe chi to the 3 times t again or something, okay? And all that we need to know are the eigenvalues and eigenvectors of the transfer matrix, okay? So indeed, we have managed to extract expectation values of local observables by doing small matrix multiplications or small tensor multiplications. We never had to grew any big object, okay? And the cost this time was not even proportional to the system size. Okay, we assume translation invariance, and just assuming translation invariance, we get rid of the dependence of the cost on the system size. Okay, so that's great because we went from exponential cost to constant cost. Okay, and that allows us to directly study the thermodynamic limit. Okay, so tomorrow we'll continue investigating properties of the matrix product state.